As we said before that we are going to talk in this chapter about magnets and the properties of the magnet. We said last time that the like poles repel each other and the unlike one attract each other. So if you are approaching a north one or a north pole to the north pole of another magnet, they will repel each other, but the north to the south one, they will attract each other. Today we are going to study the new thing which is called the magnetic domains. We are going to know more about the magnetic domains and how the materials change to be magnetized materials. First, before we study the magnetic domain, we have to recall together the electronic configuration of the atoms. We studied before in the chemistry that any atom is made up of nucleus in the center, surrounding by electrons, and these electrons are arranged or distributed in the sub-levels. When they are distributed, they have to pair together and cancel each other because each one span opposite to the other one. One pair or one span up and one span down. So in atoms containing many electrons, the electrons usually pair up together. They span opposite to each other, causing their fields to cancel each other. For this reason, some materials, they are not magnet or magnetic materials, but also for this reason, in some other materials, such as iron or cobalt or nickel, the magnetic fields produced by this electron span together, not canceling each other completely. They not pair up or they don't cancel each other. That's why we call them ferromagnetic materials. As we can see here, in the non-magnetic materials, they don't pair up, they pair up and there is no domain, they cancel each other. But in the magnetic material or the ferromagnetic materials, there is a domain. It means that they are arranged together or oriented together, but they are not lined up. That's why they will be attracted to the magnet, but they will not be a magnet. But once a magnetic field hits it or approaching it, it's going to make it align or arrange it in the same direction, align up together. That's why it's going to be a magnet. So in the ferromagnetic materials, the strong coupling occurs. Yes, they are going to pair up together, but in a large group or form larger groups of atoms whose net spans are aligned. These groups now are called magnetic domain. For example, if we have unmagnetized substance, the domain are going to be randomly oriented or arranged as we saw here in this one, the first figure on the left side. But in the magnetic material, as we said also, they are going to arrange together but not lined up. So when the external magnetic field is applied now, the orientation is going to change of each domain and slightly to more closely align, then it's going to return or being a ferromagnetic materials or a magnet. Some materials, they can be changed into permanent magnets, as we saw in the previous one, when the magnetic material is struck or had by a strong magnet for a long time, are going to arrange its domain and align it. That's why it's going to gain magnetism or being a magnet. But note that this process can be reversed again or returning back to its original type. Like if I have a piece of iron and I changed it or it became magnetized, I can change it back to a normal one by heating or cooling or by hammering it, because this actions is going to cause the magnetic domains to jiggle together and lose their alignment. That's why we have different types of magnetic pieces. We have soft and hard magnetic pieces. Based on how do they keep or retain the magnetism inside them? How do they keep or being a magnet or magnetized for a longer time? The soft one or the soft magnetic materials such as iron now, as we said before in the previous slide, they can lose their magnetism easily by hammering or cooling or heating. That's why we call them soft magnetic materials. So, due to the random action or motion now of the particles in the material, they change the orientation of the domain back and it's going to be a magnetized state again. But in the hard magnetic materials, the domain alignment persists after the external magnetic field is removed, so it's going to retain the magnetism inside it or keep it inside it without any change. So once they are magnetized, they tend to retain their magnetism, keep it, and prevent any change happening or returning back to the original state, such as cobalt and nickel.